In the last class, we had started looking at networked embedded systems, and we have studied a special purpose protocol, CAN protocol, for connecting embedded microcontrollers in an application specific fashion. Today we shall look at other protocols which are used with the embedded systems. Typically, you may use or decide to use multiple processors for an application where the computation load is high. Even on SoCs, you have seen that we integrate multiple processing elements. To offer interconnectivities to these processing elements in SoC, in many cases, a network is built connecting them. An example is multiple DSPs which are connected by a high speed network for doing signal processing applications. So here what we have shown is direct connectivity. In fact, there are 4 DSPs and one DSP is connected to, if you see, 3 others. So they can carry out, if required, parallel communication with 3 other DSPs. Typically, such a facility is provided on one DSP processor that we had studied earlier, that is SHARC. SHARC has link ports. It's not that all SHARC processors will have link ports. Particular variants do have link ports, and if they have link ports, they can have at even 6 such ports. A link port has 4 data bits that can be clocked twice per cycle. So effectively what you are providing is 8 bits of data transfer per clock cycle. And these data transfers are packed into 32 or 48 bit words. Each link port is associated with link buffers. These link buffers contain the data which is to be transmitted. And you can use DMA to transfer the data to and from the link buffers. These link buffers are typically half to play. In fact, for SHARC, these link ports are half to play. So that means one of the processors can transmit along a link port and the other processor is expected to receive data on the corresponding link port. Both of them cannot transmit simultaneously. So we need to turn these ports around. That means modalities of operation of these ports have to be changed, and this change has to be done under software control. Typically, a protocol can be used which is a token based protocol. So the token identifies the processor that can write the link ports, and the token is stored in a particular memory location local to that of the processor. And in fact, these processors are also not sharing any memory among themselves. At startup, one processor is given token by default. On completion of a message transfer, which may involve a sequence of 8 bytes, token can be passed to the receiver. When the token received by the receiver, then receiver will change mode and become a transmitter. So that's how the turnaround can be done using the token. Obviously, under such situation, the care must be taken to avoid loss of token or even replication of token. In fact, the token ring network is another network, although which is not used in the context of this kind of multiprocessor connection, but token ring network is also similar in concept, in which a token is passed around. A system or a processing element which has got the token, that gets a slot for transmission. So conceptually, here if you understand, this token is establishing the basic protocol for transmission and reception. In fact, what we had discussed, this is a specific to a set of processors, and in fact when we are integrating multiple processing elements onto a chip, these kind of networks are set up with the network specific protocol design for implementation on the corresponding SoC. In many cases, you may also find cross bus switches implemented in the silicon to facilitate communication between processing elements. Next, we shall look at general purpose network protocols. What is meant by general purpose network protocols? This is a term which we use for indicating the network protocols used for connecting the computers, general purpose computers all across. And why would we like these protocols to be implemented in the embedded systems? Definitely for providing connectivity to embedded systems with networked computers. And these connectivity may be within a local area network, maybe over a wide area network. The common data link layer protocols which are used for establishing communication over serial links are SLEEP and PPP. Okay. In fact, SLEEP is an example of point-to-point protocol. So, they are, and when they are communicating, if two systems are communicating over a standard telephonic communication line. SLEEP can be used for connecting one computer to another computer via modem even. And typically for embedded systems, you will expect that if it is provided with a serial port or an USB port, this SLEEP builds on the protocol for this kind of connectivity over any kind of serial port that is provided in the embedded appliance. What are the features of SLEEP? It is obviously point to point, and it encapsulates data in SLEEP frame for higher layer processing. In fact, this is a data link layer, so there will be data framing. So, that data framing format is defined by the SLEEP. Interestingly, this supports provision for header compression, because what is expected when you are communicating via serial point to point link, the available bandwidth will be small. So, you should have support for compression of the header of the packets. But the SLEEP, the basic disadvantage of the SLEEP is it does not support any kind of error correction. If you remember with the CAN, I said that there are error correction, and that becomes also part of your data link layer functionality. If you look at the other protocol PPP, these supports dynamic IP address assignment. This dynamic IP address assignment cannot be done through SLEEP protocol, and it also supports authentication, so that a minimum security feature, end-to-end security feature can be implemented. If you look at the packet switched network in general, Ethernet is the most popular packet switched LAN technology. It works in typically bandwidths of 10 Mbps, 100 Mbps, and even today you have got gigabit Ethernets. And it can have maximum bus length of about 2500 meters. Typically, the whole calculation can be that the segments individually can be of 500 meters with repeaters built into them. Commonly, bus and star topologies are used to connect hosts. Hosts attached to network via what we call Ethernet transceiver or hub or switch. Therefore, all the hosts which are connected via bus can therefore listen to what is going on in the bus. Okay. So, a host can detect line state, that is the state of the common line connecting the hosts, and accordingly decides to send or receive signals. But what is fundamentally different from CAN is that nodes are not synchronized with respect to the a universal clock, in the sense that if you remember in CAN, all the nodes which are intending to transmit a frame will start transmission at the same time. And so, using the principle of dominant beat, we can resolve conflict on the basis of the priority value of the identifier. Here in Ethernet, at any point of time, any node may decide to transmit bits. This is the basic difference of Ethernet with respect to your CAN or even other buses like your I2C. And therefore, all hosts on an Ethernet are competing for accessing the medium. Okay? So, this is a basic conflict scenario which needs to be taken care of. So, as we have already stated that these hosts are all connected to the common link, by definition is a broadcast protocol. Any signal can be received by all hosts, and switching enables individual hosts to communicate. Now, network layer packets are transmitted over an Ethernet by encapsulating into what is called Ethernet frames. Okay? And Ethernet frame format is something like this. If you look at this packet or the Ethernet frame format, you will find that here you have got a destination address, you have got a source address. So, by using the destination address, a processing element or a computer would know whether the packet is intended for it or not. So, a frame frames typically also has a preamble which is of 7 bytes, and it is used to synchronize receiver before actual data is sent. That means, receiver on receiving this information. So, all of these elements which are connected to the Ethernet can ready itself for receiving the data. The address is a typical 48-bit unicast address. So, this is an example, and each manufacturer can associate its own address. Now, if it is to be broadcasted, then you use spatial address. For multicasting also, you need to use spatial address. So, once this address is changed, then the hosts listening to this data would understand whether it is intended for multiple receivers or intended for a unique receiver. And body can contain up to 1500 bytes of data. Now, Ethernet's MAC algorithm is the most interesting feature of it, because you need a mechanism as part of this protocol, a mechanism for moderating access for nodes on the shared medium, okay? And that basically defines the MAC protocol, okay? Media access protocol. Ethernet uses CSMA CD, okay? Now, obviously, this protocol is different from your CAN protocol, because it actually resolves the conflicts on the basis of priorities. So, that part is not straight away coming in here. So, what is the basic protocol? If line is idle, that means no carrier is technically sensed, send packet immediately. The upper bound of the message size is 1500 bytes and must wait 9.6 microseconds between back to back frames, because that gives a basic time interval. If the line is busy, wait until idle and transmit packet immediately, and this phenomena is called one persistent sending. If collision is detected, stop sending, jam the signal and try again later. So, when there is a collision detect, what do? You withdraw and then try later on. So, that is why we say that this is collision detect protocol. So, let us look at the state diagram of the corresponding protocol machine. So, when you have a packet which is to be transmitted, packet is what? A frame according to Ethernet format. You sense a carrier and you can send, but you should also detect for the collision. So, if you detect a collision, what do? you go back, okay, that means you detect a collision, so it cannot send the packet, and again you go back and retry. That is, there is no collision, so the next packet can be sent without any problem. If there is a collision which is detected, then you jam the channel in the sense that you do not send the packet. You calculate a parameter called B, we shall see how this parameter can be calculated, and you make subsequent attempt after a waiting period. Now, if the attempts, what we say, is less than 16, there can be an upper bound on the number of attempts. Then you go back and try sending the packet again. If it is more than 16 or equal to 16, in this case we are using this number as 16, you basically discard the packet and report an error. Fine. So, this is the basic state diagram for CSMA CD, which is followed by Ethernet. Now, the interesting feature is of how do you back off. That means, when you detect a collision, how do you decide what will be the next time instance for transmission. So, the delay time is chosen in a random fashion. In fact, there is a choice of k, and on the basis of the choice of k, okay, you randomly make a choice of k, and that defines the delay. This is an exponential back off, okay, because the back off time changes and increases. Okay. So, the maximum value of k can be 1023, and you can give up after several tries. What we say that in this case, what is important to note, this value of k is randomly chosen. So, the delay that is applied is a random delay. So, why delay is random? Because if there is no random delay, then there is a chance that sources would retransmit in lockstep. That means, they would again land up into a collision. And why not just choose from a small set for k? This works fine for a small number of hosts, but if the number of hosts increases, then large number of nodes would result in more collision with a small number of k, and that is why I use larger number of k. Now, what is important to note for as an embedded system designer, that because of this random wait parameter getting involved, the performance of Ethernet is not completely predictable. Okay? Because if I want to have any real time service supported on Ethernet, I would like to have predictable performance. Because of this exponential back off with a random selection of delay, the performance of Ethernet is not strictly predictable. The MAC algorithm from the side of the receiver is very straightforward, because sender handles all access control. Receiver's job is simply to read frames with acceptable address. Okay? If it is an address to a particular host, if it is an address to broadcast or address to multicast to which host belongs, then it will read that frame, or if it is in a promiscuous mode, for some reason or other, it will read all the frames. So, this is a very straightforward MAC algorithm for the receiver. So, if you look at the performance, because performance is a key issue if you want to connect multiple embedded systems in an Ethernet, the problem is, as I have already stated, performance is difficult to predict due to random waiting time. And that is also one of the reasons why Ethernet's peak utilization is pretty low. Okay? There would be a conflict and there will be a random wait, and there may be time when there are no packets being transmitted on the link. And peak throughput can become worse if you have more hosts, because there will be more collisions. If you have smaller packet sizes, then the frequency with which hosts would try to send packets will be more, hence more collisions. Longer links also can be source of problem, because how is collision detected? Collision is detected on reading the packet. Okay? So, if the delay is long, that if there are longer links, collisions will take longer to observe. So, there will be an unnecessary wastage of bandwidth. Okay? So, efficiency can be improved by avoiding these conditions. So, if we summarize what we are trying to say, that quality of service tends to non-linearly decrease at high load levels. Okay, that means the delay, the basic quality of service here we are trying to talk about is, say, the delay in the packet arrivals. In fact, the variation in the delay in the packet arrivals are not really bounded. And that is the reason why you cannot guarantee real time deadlines. But if your load is less, that means if the number of nodes connected is less, may provide good service. So, in fact, you will also find that video conferencing or teleconferencing equipments coming enabled with Ethernet. So, basically you can use Ethernet for video conferencing applications when the load is less. And if the load increases, what will happen? There will be problem in receiving the data. Now, and I think you have understood how the video conferencing appliance is relevant in this context, because you have to send video as well as audio data packets, and I need to have bounded delay for the arrival of packets, because if I have bounded delay, then I can allocate fixed buffers, okay, so that the presentation is not of low quality. That means, it is not that you present one frame and next frame you present after much delay, so that the continuity is lost, your speech is broken in between. So, such kinds of problems will not occur if you know an estimate of the worst case performance of your Ethernet. But that is not always possible, and that is a basic bottleneck in using Ethernet as a basic network for these kind of application. There are various hardware implementations of this Ethernet protocol, because if there is no requirement of strictly real time constraints, then you can use Ethernet for a variety of applications. Here we are looking at an example hardware. Okay, this is an embedded standalone embedded system. Why? Because it has got 100 Mbit Ethernet transfer speed with an 8051 microcontroller. That means, this Ethernet protocol is enabled or provided with the hardware, additional hardware, as well as with a microcontroller. Okay. So, along with these, you have got 4 channels of AD converter, digital I/O, and you have got I2C compatible bus availability, then compare and capture channels. Also, it has got onboard static RAM, onboard flash, and JTAG interface for high level debug. Now, these kind of products are there today available. Why they are available? You can add on such a card to your appliance and very easily provide Ethernet connectivity. If you see, it has got I2C compatibility. So, using the I2C, you can connect it to your main system, okay, and you can have data transferred to this kind of a small footprint device, so that you can plug through this card your appliance to an Ethernet port and have Ethernet enabled connectivity. Now, in this case, the basic protocol here gets implemented on the processor. There are also devices and appliances where you build the stack in the hardware itself. Okay. So, the entire stack gets built into hardware, maybe using an FPGA block, which enables more efficient implementation of this protocol. Okay. So, at a low cost, you get a module with a small footprint which you can add to your appliance. Next, we shall look at Internet protocol, which is actually the basis for today's Internet. Internet protocol is, why it is called Internet protocol? It provides an inter-networking standard, that is connectivity between two Ethernets and a token ring network. We had already referred to a token ring network, where basically a token is passed around the processing elements, okay, and when the token is available with the processing element, it can transmit data. And higher level services are built on top of this Internet protocol. Now, the internet protocol basically implemented through a router when you are connecting two distinct networks. And IP works what we say at the network layer. So, at the network layer, the IP protocol creates packets for routing to destination, and in fact a node that transmit data to different types of networks is called a router. So, router may not have top layer protocols implemented. Its basic job would be to receive packets and route the packets to the respective networks depending on the destination address. So, a packet on its path can pass through many routers, and in fact there may be packets originating from one destination, but two consecutive packets may be put onto two different routes by the router itself. Okay? And that is the basic reason why we call this a packet switching network. Packets are switched from one path to another path. And you can also realize that if this kind of packet switching takes place at a particular node, this node needs to handle pretty high computation load. Okay? Because if you are looking at 1 gigabit Ethernet, then switching at the node has to meet that speed of the backbone. IP packets have got information like version, service type, length, source and destination address, as well as data payload, and data payload can be maximum of 65,535 bytes. The addresses are very well known. Okay? It was 32 bits in early IP and 128 bits in IP version 6, and typically written in this form. There can be the number of digits depending on the addresses that are getting allocated, and you have got the domain name server which transforms this kind of symbolic addresses to actual IP addresses. Please note that these IP addresses are different from that of your Ethernet addresses. Okay? So, Ethernet addresses are provided at the manufacturer's level. These IP addresses are provided at the network administrator's level. Now, when the routing takes place, what we say, this is a best effort routing. So, there is no guarantee for data delivery at IP layer. So, even when the routing is taking place and router is routing the packets, it will try to match the availability of the bandwidth, and it is a best effort. So, there is no guarantee. There is no guarantee that packets will be delivered with regard to a deadline. So, routing can vary from session to session and even packet to packet. Okay? And if you are really looking at multimedia data transfers over such a network where the deadline becomes important, you got to have additional protocol layers implemented on top of them to have efficient routing. Now, how is this routers really implemented? In fact, routers are again examples of embedded systems, because routers do have processing elements, but they are not really general purpose computers. Their basic job is to receive packets and route packets. So, you have got network processors which have been used for implementation of these kind of routers. So, basic job of a network processor to offload packet processing and routing load. And in fact, you may also find that for a general purpose application or general purpose computer may have a network processor card which is functioning as a router. So, your main processor may be offloaded of this task, that also is possible. Also, you can have standalone routers as well. So, the architectures of these network processors which are targeted for use in routers, the basic focus is to exploit parallelism to accelerate switching of packets, maybe from one protocol stack to another. We have considered an example of routing of packets from say one Ethernet to another Ethernet. Okay? There is one Ethernet network to another Ethernet network, but it can be from one Ethernet network to a token ring network. Then there has to be a protocol translation, because protocol of Ethernet is different from that of a token ring. So, your packet headers have to be stripped, the packet has to be reframed so that it can be put onto another network. So, that job is to be handled by the network processor. So, what you find is that there are basic objective is to use exploit parallelism to take care of this need. One very important part of this routing is table lookup for address translation, because on the basis of the address you need to know where the packet is to be sent next. So, address lookup or even the routing table lookup, if you already are maintaining, the routers in many cases maintain the routing tables. Maintenance of routing table requires facilities for very fast table lookup. Okay. So, if such a facility is implemented in hardware, it becomes easier and more efficient. So, you have got specialized hardware for table lookup. Also, these architectures are multi-threaded architecture. What is meant by multi-threaded architecture? It means that in the hardware itself there is a support for individual threads. So, you can associate a thread with each packet, okay, and the whole system itself behaves, that is your processor behaves in such a way that it is handling a thread independent of other thread. So, if you remember, when thread is implemented through OS, operating system keeps track of the thread, keeps track of the PC. But here when you have a hardware support, the hardware itself provides the bookkeeping tasks, okay, meets the bookkeeping requirements for managing multiple threads. And if you can have one thread per packet with less overhead for context switching, you have actually doing what? Meeting the requirements of receiving each packet and putting it to another network depending on the requirement. So, the router looks something like this. What we have shown here is a router consisting of multiple modules, not just a single module, but multiple modules. And these two blocks are taking care of your physical layer requirements as well as MAC protocol, which we had already discussed, because router comes at the network layer level. So, you have got your local memory, okay, and this is a DMA subsystem. So, the DMA subsystem will do the transfer from say a packet memory to the MAC, okay, on the bus, and here the protocol processor need not be involved over the actual data transfer. What does a protocol processor would do? Protocol processor can do protocol translation, I have already told you. It can also do what? Actual finding out the route for the packet. And these modules are connected via interconnection block. So, what you find is that each module now can operate independently, okay, and that gives you the maximal parallelism for the packet processing. Okay. So, these two architectures are identical, and depending on what is the speed at which you would like to work, there can be multiple such modules being made use of. And in fact, all these routers are nothing but examples of your embedded systems. TCP is a transmission control protocol, which provides connection oriented services, that is from source to destination the complete connection is provided by the TCP layer. If you remember, what is IP doing? Getting a packet, routing it in different way. But where is the origin of the packet? Packet's origin is at an application. Now, with respect to the application, the transport control protocol TCP maintains the connectivity with that of the destination application. In fact, there would be other layers from where the packets would generate and other features would be managed with respect to the packet, but connection oriented management is primarily done by the TCP protocol. So, the first job is to make sure that the data arrive in appropriate order, because since packets are put into different routes, packets can arrive in different order. They have to be assembled in correct order, that is the job of TCP. It also uses an acknowledgement protocol to ensure that the packets arrive, but however, there is no guaranteed quality of service. Okay, guaranteed quality of service is again very simple quality of service that you are looking for, maybe a bound in the delay for the packets arriving. And in fact, one parameter which we refer to as jitter, there is variation in the delay. So, even if you have the variation in the delay bounded, then also there is a QoS guaranteed. The TCP really does not guarantee quality of service. On top of TCP, basically applications are built. So, here the basic model is you can have a file transfer protocol. This is your HTTP protocol, hypertext transfer. This is your basically mail protocol. This is a telnet, remote login protocol. This is for UDP, user datagram protocol, and this is simple network management protocol. So, these are various protocols, top level protocols which sit on top of IP and TCP and IP and UDP. In fact, today you will find that many of your embedded systems really have support for your HTTP protocol implementation, so that you can access those devices over HTTP link from any computer. So, what is the advantage of that? Advantage is if you have a web browser, you can access and monitor a remote device. So, let us see some examples. So, you can have network enabled storage devices. Okay. We have typically found that I have got a hard disk, okay, or a magnetic tape which is typically associated with a computer. It need not be so. I can have a hard disk with a embedded system attached to it, making it a network enabled storage system. So, the data storage now takes place over a network. So, you can have, say for example, in your home a network enabled data store, using which you can store maybe a TV program which you are receiving in a digital format. You may also store your telephone directory from your PDA using a network. Okay. So, then these storage devices becomes standalone devices if they become TCP IP enabled. Okay. So, you use TCP IP to transfer data to and fro from standalone devices. Okay. So, this protocol gets implemented. I have already shown a module for implementation of Ethernet. On that similar module, you can have the complete TCP IP implemented, and you attach that to a hard disk hardware, you get a effectively an networked storage system. Then you can provide Ethernet connectivity as well as TCP IP connectivity for monitoring and controlling instruments. You can have a radio frequency amplifier which are used for say broadcast or other applications. Now, you want to monitor its condition, you want to set parameters to the RF amplifier. How to do that? Okay. You can have a digital interface. If you have a digital interface, then using the digital interface you can do a remote connection, and through the remote connection you can provide these features. Okay. And other example is an UPS. If you want to monitor battery life of an UPS remotely. Okay. So, what you provide? You provide a TCP IP as well as Ethernet enabling feature. In fact, if you remember, we had seen an example of a vending machine, okay, which is Ethernet enabled, so that the complete stock monitoring can be done from a remote location. In fact, on these devices, if they are really implementing TCP IP, on top of TCP IP you may find thin web servers, very basic web servers implemented. Okay. And why web servers? Because if I am using a web browser, any computer which has got a basically a web browser, I can use that web browser to connect to these devices. Okay. So, if you have a web server running at the device, then I can connect to those devices using my browser, monitor its conditions, set their parameters. So, I get a complete facility for remote monitoring and remote controlling of any equipment. In fact, that is the major application of Ethernet and TCP IP for in the embedded domain. So, we get with these what we call internet enabled embedded systems. This class of devices are also known as internet enabled embedded systems. And any embedded system that includes an internet interface, you can have even a refrigerator, okay, and on the refrigerator you can set the temperature over the internet. So, you need to have now a home server, a thin home server. You can have internet appliance which can be an email device. In fact, there are email devices which are standalone email devices, and in fact there are devices which has got a pen interface. Okay. So, a standalone email device with a pen interface. So, instead of typing in, you can actually write letters and send it via email. Okay. So, that becomes what? Effective implementation of on top of TCP/IP your mail server. Okay. There are other examples like laser printers, personal digital assistants, home automation system. Refrigerator is an example of that. So, you can have your geyser connected via internet, you can have your microwave connected via internet, and you can control everything before you when you reach home. You can set the temperature on the geyser while you are driving. So, that is a basic model that being talked about in this context. Let us take an example, a Java cam, that is a remote visualization. In fact, today you get more sophisticated systems. You get cameras which you can control. It can do a pan tilt control you can have over the internet. This is a very simple straightforward implementation around a processor which is more like a 486 classical 486 processor, which can support about 1.5 megabytes of memory, and it has got a parallel port interface. And what it uses a memory efficient what we say Java nano kernel, which is something like your Java KVM or Java virtual machine which we intend for usage on your small handheld devices. So, effectively what you have, this is your camera, and you implement a server, a quick cam server on top of your Java virtual machine. Okay. And at the web browser you can have an applet. So, you download that applet establishes connection with the quick cam server, and you basically get the images downloaded and see what is happening from standalone camera. Please keep in mind that this is not a webcam in a classical sense where you connect the webcam to a PC. This is a standalone Java camera. Okay. So, effectively the HTTP server is implemented on top of this simple 486. Okay. So, you put it anywhere, you do not need a computer, okay, just plug it onto a TCP/IP socket and you can do a communication and see pictures. Even if you have the wireless Ethernet, then this can be an wireless camera. In fact, commercially such wireless cameras where you can do pan tilt control are available today. So, this takes us to what is called wireless LANs. So, wireless LANs are obviously enables you mobility, flexibility, and this is expected to be used where the wiring is difficult to be done. Okay. And the basic configuration you look at is we say a single cell wireless LAN. So, the basic idea is that you have an Ethernet, you have an Ethernet connectivity, this is your basic backbone, okay, and this is your Ethernet switch, and you can have all these systems connected via wireless link. So, you have got a cell, a single cell, and this single cell wireless link which is connected to your 100 Mbps Ethernet switch, and other devices are connecting to this single cell. Okay, this can be from a switch or from any of these standalone systems. There can be also multi-cell configuration. So, here you have got multiple cells and you have got systems connected via these multiple cells, and each of the cells communicate using maybe its own frequency, okay, and then each of these cells are connected to the backbone Ethernet switch, and so that provides connectivity of these devices to your basic network. This is a basic conceptual model of the wireless LAN. This wireless LAN provides what we call nomadic access, link between LAN hub and mobile data terminal. So, you can move around with your laptop or notepad. Also useful in extended environments such as campus or cluster of buildings. Users move around with portable computers and may wish access to servers on wired LAN. Okay. In fact, we have such networks in this institute itself. Also today you will find that airports and others are becoming this kind of wireless LAN enabled. So, you get a nomadic access using your laptops or even your palm tops. So, basic infrastructure wireless LAN is conceptually this, that you have got a high speed backbone wired LAN and these are the cells, and you have got these basic nomadic stations. You can move from one cell to another cell, okay, and when you are in any of the cells you can access all the servers which are at the connected to the infrastructure backbone. The other aspect of this is ad hoc networking. So, in this case you do not talk about a backbone, okay. You are basically trying to set up the network among these individual stations themselves, okay. So, it is a peer to peer network set up temporarily to meet some immediate need. It can be a group of employees, it can be a network for duration of meeting. So, if you look at that wireless LAN therefore provides for what? Provides for connectivity where wiring is difficult, provides for connectivity in a nomadic fashion that you can move around, also provides a facility for ad hoc networking. That is a set of stations suddenly coming together and setting up the network on being discovered by each other. The basic technologies is infrared LANs, spread spectrum LANs and narrowband microwave LANs, and majority of infrared LANs, very simple infrared LAN we have already looked at. This IRDA protocol can be used for that purpose, and majority of the LANs that we shall look at, okay, and we have today are spread spectrum LANs. Narrowband microwaves are also used for this purpose. The most well known LAN technology is 802.11. In fact, whatever applications we have talked about using Ethernet today, they are getting transported on 802.11. Okay, you would like to control a device, say an RF amplifier or an UPS. Ideally, you would like it to be on a wireless LAN. So, you are not consuming a Ethernet port. Okay, you can place it anywhere in the lab and you can connect to it in a remote fashion. So, 802.11 basically provides a MAC protocol. Okay, and it uses unlicensed frequency spectrum 900 megahertz or 2.4 gigahertz, because these frequencies when you are using you do not need to take licenses, because other frequencies are preserved and reserved for various applications like TV transmissions, defense communication, so on and so forth. This uses spread spectrum. What is spread spectrum? The signal, the baseband signal is distributed over wider frequency than that is required. And in fact, typically for all these use multi-hop spread spectrum. That means you use multiple frequency slots. Okay? So, you have got a random sequence of frequencies and the data is spread over these frequencies, okay, a number of frequencies, and how they will be distributed, that is also a random, because that minimizes the problem of interference, because these are to be used in a kind of a variety of scenarios. So, there can be source of problems and noise. So, you would like to make it interference resistant. So, that is why the spread spectrum frequency hopping is used as a physical layer specification for these kind of networks. So, the basic architecture is what you have: a basic service set or a cell which contains wireless host and access points. Okay. These access points can be connected to a wired LAN. Okay. So, basically the base model that we have already shown you, and BSS combine to form what is called a distribution system. When you have an ad hoc network, stations can, then what is happening? You are really not having an access point. Okay. Access points is more of an infrastructure network, okay, which is providing you nomadic access. So, dynamically form a network without an access point. In fact, there are these IETF managed mobile ad hoc networks, and there are these protocols which are built on top of this 802.11 to enable this kind of ad hoc network setup. So, what is the basic MAC protocol? Okay. It is CSMA CA, that is collision avoidance and not collision detection. This is a basic difference. If you see that we are looking at variety of these MAC protocols, CAN, Ethernet, now 802.11. Now, what does it do? If sense channel idle for some diff second, okay, there is some bound diff second, then transmit entire frame because you have not detected any collision. If the channel is sensed to be busy, then you do a binary back off, okay. And receiver, what it does, if received okay and return acknowledge after a certain time period, which is SIFS. So, this is a very basic description of the MAC protocol. I am not going into the details. This is a very basic description of the MAC protocol. So, effectively what we are doing is that the source, after the diffs, it senses the channel. If it finds a channel to be idle for about diff second, it sends the data. Now, destination waits for shifts this second, okay, and there is no data, then it sends the acknowledgement, okay. The others defer access using what is called NAV, okay. What is your NAV? NAV is called network allocation vector, okay. So, 802.11 frame has transmission time field, okay. So, there is a specific transmission time field, and others what they do on hearing the data defer access for NAV time units. They defer access for NAV time units. So, when there is a collision, if you look into it, what we are doing, what we are telling is that it is not the collision detect, it just senses whether there are activity on the network or not, okay. If there is no data being transmitted and if that observation is made for a fixed time period, which is your diffs, then only the transmitter starts sending the data, okay. And then what it happens? The receiver sends back the acknowledgement after a certain time period. Now, others, what will others do? Others will defer, that is on hearing the data, defers access for a certain NAV time units. This NAV time unit is called network allocation vector, okay. So, this network allocation vector is associated with the nodes, okay, and they provide for this this deferring time period. So, it is not like a exponential back off. So, the back off is with regard to a NAV, that is the defer time period which is specified through NAV allocation vector. And 802.11 has got transmission time field, okay. So, transmission time field also tells you that the time required when for such a transmission is taking place, okay. So, effectively here there is no collision detection, what you have got is a collision avoidance, okay. Why? Because if you have a collision detection, if you look into it, one very interesting feature you should know is that collision detection means you are actually using energy to transmit and then detecting the collision. So, when it is a wireless link, you would like to preserve energy. So, why would you like to transmit the data and detect the collision? Okay. So, this is a very basic motivation you can realize why this protocol should be around collision avoidance. And in fact, today you will find that this kind of I already gave example that what if we have 802.11. So, on top of 802.11 you can have, if I see there is an infrastructure network, okay, through an access point, you can have what? You can have the entire protocol built, okay. So, if your 802.11 is available on a device, okay, so effectively that device now becomes part of your LAN and it can be moved around. If it is basically if it is a nomadic access, particularly important for your appliances, because really you may not like appliances to set up ad hoc network. What you would like for appliances, just like a testing equipment, okay, or a instrument, okay, or even a device like camera to be taken all around and still have network access, okay. And that is precisely the basic motivation of enabling this wireless network on variety of devices and embedded devices today, okay. So, basically they implement this 802.11 MAC protocol and they implement the spread spectrum communication to meet the requirements of physical layer specification. On top of that, higher layers can be also implemented and provided for. So, example of a camera would be what? You have got even HTTP server implemented on such a camera, and that camera has got at the lower level your wireless link. So, that brings us to the end of today's lecture. So, what we have studied today, we have studied inter-processor networking, learnt about wired and wireless LAN protocols and explored use of these protocols in a variety of embedded systems. If you have any questions. See, the question is, in 802.11 do we guarantee there won't be any collision at all? It is not so. Okay, there would be obviously collision because there are multiple elements, okay, or multiple stations which may like to transmit at the same time. But what is important is, in terms of protocol, each station senses a carrier, and if it is find that nothing is getting transmitted, okay, then only it starts transmission. So, it is a collision avoidance. So, if it finds, see, the basic difference is what? In an normal Ethernet, you actually detect a collision. That means you sense a carrier and you send the data packet and detect that there is a collision. So, that packet is not what is being sent, and hence you should back off. So, you should jam. In this case, it is not happening that way. It is detecting that there is some activity on the channel. So, it basically has to defer its activity. How long it would defer? That depends on NAV allocation. Okay. So, that is why it is a collision avoidance.